Good afternoon. We're going to show a borehole image workflow for processing and uploading conductivity derived grain size information. And I hope it's of interest to you. The outcomes of this will be a grain size and a pore throat size distribution, which we'll illustrate on a map. And we'll also show you maximum permeability orientation and how that can be derived. The methodology involves taking image textural analysis output for each formation, but we're going to specifically focus on one formation. Finally, by putting this data on the OSDU, or the Open Subsurface Data Universe, it allows multiple disciplines to use this information, and it can be quickly reviewed by teams anywhere in the world. And I think that's an extremely important facet of the OSDU. The OSDU is a cloud-based storage scheme, which you all know, and the workflow we're presenting is extracting data, performing a multi-well analysis, and then uploading the results. We're going to use the AWS 47 lining OSDU instance for this. So thanks to them for allowing us to use that instance. The first step in the objectives is to download the conventional image data, perform a petrophysical evaluation, perform the textural analysis, which involves porosity, permeability, grain size, and orientation. And then finally, we're going to upload the data. The workflow involves initial ingestion, we'll show you that, download specific wells, perform petrophysical evaluation, textural image data analysis, data upload, and then we'll finally show you data verification as, say, a geologist who looks at this analysis would want to do. There are some assumptions. The data has been top and tailed, SP drift corrected, and so on and so forth. So the first step is data ingestion. So we start by showing you how we get access to the OSDU. So we go to the OSDU button, and if we want to add a new one, we go in here, we give it a name like AWS, and then we put in all the information like so. We can access AWS or Azure or whatever, and then we just click on that to open it, which we'll do in a minute. Once in there, you can circle a bunch of wells, and then we go back to the OSDU and we connect to it. And then we're going to say we want to upload. So this is the process of ingestion as using DDMS. So I go in there and I can select the projects, or I can do a custom selection. And I can choose from DLIS, LAS, or archive. And I load the data in, and it starts off like so. We use the search button, and we're going to search using a polygon, and we draw a box around the entire area that we want to search, and then we hit OK because we don't really know what log we're going to search for or what formation, and we basically wait for it to come back, and it comes back with the wells, and they're in there. So we can zoom in to the selected wells, to the wells or all the wells, and then we can choose one of the wells and download it, and we'll talk about that next. So we're going to download the data from the OSDU, and hypothetically we have to do the petrophysical evaluation, and then we have to do the textural analysis. So we'll describe that next. So when we're downloading from the OSDU, we go to the OSDU connector, and we choose the Amazon 47 lining connector. And it brings up a map. And then we just need to search using a polygon in the area where we've got the wells. So we draw our polygon like so, and we hit OK. I'm not going to enter any particular parameters in there, and it will bring us up a list of the wells. Once the wells are selected, we then can zoom in on them, which we're going to do here, and then we can select all of them and download them. Once they're downloaded, we then dismiss the OSDU interface, and we see the wells are here, and we go to the map view and we select the project, and as you can see we've got them there, and we go to process and we just do the processing, and then as you can see we've got the results of each of the wells, and we then want to see what they look like in sections, so we create a section from southwest to northeast and we display it here. And as you can see, we've got the section, and we can move through the section and look at the wells, look at the intervals. We can also change it so that it's hung on a particular formation, so it's nicer to look at. So the processing involves accelerometer correction and so on for the image. We then mask out bad features, and then we use a bad hole logic as well in the processing. Where we produce the textural map, we're taking the conductivity, and we're basically using a point close to but not including cemented bands, hydrocarbon and so on. And on the other side, maximum conductivity, we don't really want to get all the shales in there or the mud effects, so we choose a point there. And then from all the buttons we produce a textural image, which is on the right, that shows increasing grain size to the right, and the sorting is the width of the VDL. Defining your conductivity range for the textural analysis is important, and each of the tools in the market will have a different resistivity or conductivity range and scaling. So we choose the textural analysis points based on those tools and the manufacturer that makes them unique. We've done a study that's documented in some other papers of over 100 wells, and they covered water-based, oil-based, and all the various different manufacturers. We go from the image or the conductivity data to a textural map, and then from the textural map through a proprietary algorithm we produce a phi scale, and then from the phi scale you can go directly to grain size, and then from that you can actually bin the phi scale and produce volumetrics and a lithographic representation of the section. With porosity, we calculate the porosity using broadly an inverse Archie equation, and when we combine that with the textural map we can actually turn it into a permeability. Again, we have a proprietary algorithm for doing that, and we also produce pore throat size from that. Once we've got that information, one other thing that's interesting to do is to actually calculate the permeability azimuthally around the image, and then from that we can identify the orientation of maximum permeability and present that as a polar plot. And I have polar plots on the right for the various wells that we're doing, 5 wells in total. And we've got walkout plots showing the orientation of the maximum permeability, which is interesting to do. So we've produced the results and we're happy with them, and a geologist has asked to integrate that into his work. So the next step is what we're going to do is show you how to upload that to the OSDU so the geologist can access it. So once we've done the processing, we've done the petrophysical and the textural analysis, we go in to the map view and we choose the wells. Then we go into the OSDU and we choose AWS 47 lining. And we upload the data like so in the normal fashion. And once it's uploaded, we can review that the data is in there by simply selecting the polygon area and viewing the data, and we can blow it up and we can see the wells. So all the analysis you've done for the textural work with the image needs to be integrated with the geological model. So your geologist needs to download the data to put into his model or to review. And that's what we're going to do next. So when we're downloading from the OSDU, we go to the OSDU connector and we choose the Amazon 47 lining connector. And it brings up a map. And then we just need to search using a polygon in the area where we've got the wells. So we draw our polygon like so, and we hit OK. I'm not going to enter any particular parameters in there, and it will bring us up a list of the wells. Once the wells are selected, we then can zoom in on them, which we're going to do here, and then we can select all of them and download them. Once they're downloaded, we then dismiss the OSDU interface, and we see the wells are here, and they're in a list, and we can look at them in a map view, and then we can select from that map the wells again, and we can play with them and do functions such as histograms and so on to look at the information. And we're going to set up to look at the median grain size, which is grain size P50, and we're going to look at that and show the histogram of that for all the wells, superimposed one on top of the other. And when you see that, you'll see that you can see a difference, and then we can show that by formation. So I'm going to look at that grain size by formation E, and you can see that you've got difference in the grain size. And then we can actually plot that out as a PDF and show that, show the wells side by side in a PDF plot. So we do that, and here's the PDF plot showing the different grain sizes. We can then move on, and we can do the same thing with pore throat size, which I've got here, and we can scroll through the various formations that we've got set up, and you can see that. Once we've done that, we can then go and look at the wells in cross-section so that we can actually see what's going on. So basically we go here and we set up a cross-section from southwest to northeast, and we plot the data and we look at the cross-section which I've got here, and if I expand it, it's there. And that's one to see the data in one go. So this cross-section is extremely busy, and on the down in the bottom right-hand corner I've got the header sort of blown up, and we've got the conventional logs and the images on the left, and we've got the distributions in the VDLs on the right-hand side, going from porosity to grain size to pore throat size and permeability, and then the permeability azimuth. And we show that in, I've shown a blow up of the first well so that you can actually see the permeability orientation. So that's one way of looking at the data. If we look at them, look at the grain size of the wells, and I should say that the Caliance wells down here and the Tarosa wells up here are about 80 kilometres apart. So we can actually see that we've got a variation in the grain size with the Caliance wells, and particularly Caliance 1, showing a very large grain size as opposed to a much smaller grain size in the Tarosa area. This translates into a pore throat distribution that also increases from Tarosa to Caliance. We've got plotted on this the pore throat distribution, the histograms plotted 0.1 to 100 microns, and we've also got the polar plots of the permeability orientation. Generally, the permeability orientation is south to north, with lateral accretion east-west. When we look at the permeability, again, it's showing a similar sort of distribution. It's highly permeable in Caliance and not so permeable at Tarosa. And the directions are showing the directions as we discussed. In summary, the well groupings, as I indicated, are about 80 kilometres apart. The paleocurrent analysis, which we have from elsewhere, has the formations with prevailing south provenance and east-west lateral accretion of sands. Obviously, the provenance is more detailed in other work, but there is a lot of variability in it. The grain size in this work seems to increase from Tarosa to Caliance, but there's variability at both locations, and Tarosa seems to be more heterolithic. The pore throat shows an increase from Tarosa to Caliance, and the permeability shows similar orientations to the paleocurrent permeability. And we also pick up some orthogonal trends. By using the OSDU, we've been able to provide the data and not just select samplings of the data. We've been able to provide everything so that our geologist can interpret all the information and he can integrate it with seismic core data and engineering data. And he can do it pretty quickly. And the data can be integrated and maps created directly from the results. So I guess what I see in the OSDU, and I'm quite excited about it, is it provides a uniform collaborative environment that even dispersed people around the world can use it to evaluate and put together interpretations. Thank you very much.